So now we want to talk a little bit about the interpretation of results and presentation of results. So let's move us on. Okay, what do the estimates mean? So we've seen examples where we've estimated these model, we've got these point estimates. They might be either effects coded, where they're all relative to the mean, or they're dummy coded, so it's relative to a particular base. We've got these parameter estimates, which we're saying we're interpreting as being some measure of preferences towards the objects. So what we'd like to do is to think a bit about interpretation. Well, the first and most important thing is that those coefficients, whether they've been generated by counts or whether they've been generated by estimation, they can only inform you about relative weights of objects, relative to each other, not absolute values. Now the reason for that is that there is, on those parameter estimates, there is no absolute meaning of, say, 0. So when we do a dummy coding, we have a value of 0. That just means we're rescaling everything along the points on the line, so that actually we're sitting there with that particular item having a value of 0 and everything relative to it. If we do an effects coding, we are working out those values relative to the average of all items. So what that means is that we can't use those parameter estimates in the form of what we might call a ratio scale. So if we look at the parameter estimates, we can't actually claim that if we have a value which is twice as large as another one, that actually implies that the weight that we attach to that object is twice as much as the other. So these are relative weights on sort of a utility line. There is no base, they can't be used as a ratio scale. So there's been a proposal that you to transform the parameter estimates, particularly for the purposes of presentation and interpretation, and it uses something called the scale probability scores, the SPS, and this is only strictly valid for the conditional loaded estimates, because there we can make some interpretations, make some statements about what these transformations mean, because basically that's been estimated as a probability model, and we're going to use the fact that that's been set up as a probability model in order to be able to exploit that and in order to create these scale probability scores. Okay. What's the definition of scale probability scores? Well, it's going to be a probability P. So it's going to be the scale score P for object I, and it's simply this sort of the ratio, which is sort of familiar. It's like a logit ratio. It's the exponential of beta bar I divided by 1 plus the exponential of beta bar I. What's beta bar I? Well, that's essentially the estimated parameters defined as deviations from the mean. So if you've estimated your modeling with effects coding, that is what they are. If you've estimated them with dummy coding, you just need to work out the average of your 10 parameter estimates, work out what the mean value is across 10, 8, whatever the sample size, the number of items is, work out the average across the number of items that you have, and then just express your parameters as being mean deviations. So that's what this B bar means. It basically says we're taking deviations from the mean. What that means is that the average in some sense, the average item, which may not exist, but if you think of an item at the center of this distribution, it will have a coefficient of 0 by definition, because the parameters are estimated as defined as mean deviations. So what's this formula for? Well, this is basically the probability of picking item I as the best when we have two items in a set where the other item is an average, because that means that the implied beta bar for the average item is 0, exponential of 0 is 1, so that's why this 1 is here. So this is just working out the probability that we would have picked item I as best if it was in a set of two items and the other item was in some sense average. So this is now going to put us onto a ratio scale, because we've got some meaning now of what 0 means. A 0 means there's zero chance that you would have picked that item as best, and it's constrained at the top end by 100. So it's got some nice properties. What the suggestion is, the people who develop the scale probability scores, is to say, well, once you've created your set of these probability scores across, let's say, our 8 items, you then just rescale them all so they sum up to 100. There's no guarantee that across the items that this probability is going to add up to 100 or add up to 1 or any particular number, because it's simply the exponential of a coefficient divided by 1 plus. So this is just the probability of choosing 1 out of 2, which will satisfy the normal rules of probabilities, coefficients or scores. But across the full set of items, there's no reason why those probabilities should add up to anything. Just to normalize it, they suggest just rescale so they add up to 100. So this is the suggestion that's coming out of the Sawtooth software, the MaxDiff technical paper, which I'll give us a reference at the end. So this is back to our the data set that we've had from this project. This is the 8 items that we ask our experts to rank or to pick best and worst from, and we've got the 3 jurisdictions, Bangladesh, Nepal, India. And so now what we can do is that we can, because now these probability scores have some clear bounds and clear definitions, we can now start, say, comparing them across the 3 different jurisdictions. So a simple graph like this, and we can see, we won't deal in much detail as to why this might be happening, but what you can see is that we're seeing difference, say, in the way that India is thinking about the value of cheap inputs as a means of improving farmers' income. They're giving it a lower value than we're seeing for the other 2. There must be some compensation for that, because the bars do add up to 100 for Bangladesh, Nepal, and India. Each one within that adds to 100, and you can see that, well, the Indian experts are coming back and saying, well, actually they're putting more weight on non-farm income sources as a model. So you can see that this bar is starting to pop out above here. And consistently across all 3 groups, as in variety in crop production, or increased variety in crop production, is being seen as lower weight. So you can start to compare these measures, these parameter estimates, compare them across different groups here across 3 jurisdictions, but elsewhere we've looked in other ways of splitting the data up. So this is this idea of these scale probability scores. So they can now be interpreted as ratio scales, and an SBS, a scale probability score twice as large, means the item is twice as likely to be picked as best. One thing is, as a technical level, as in those scores are still influenced by what's known as the scale parameter within a conditional logit model, i.e. how much random noise there is. If you've got lots of noise in your data, as in your respondents are either not behaving consistently across the group, or they are just picking at random, or they're much more noisy and random, then what will happen is that those score estimates will head all towards the mean. If I've got 8 items, that's about 12.5. That little distribution, that graph, will start to, let's just slide back to that. This graph, if you've got a group who's either there's very low levels of agreement within the sample, or they are just have a lot of noise and randomness, they weren't engaged in the task, whatever, what you'll see is that will push this so that it becomes flat. So these scores are a combination of 2 things. It's a combination of their relative weights in terms of their utility values for these, but it's also includes and is influenced by the degree of certainty or consistency with which the groups are making their choices. So that's important to remember. Now, one of the interesting things you can do when you start to get these scores in that way, or you can think about these things, is you can start asking questions in different framings. So you can ask the same people about the same item, but using a different context or framing as to how you ask them to choose best and worst. So this is a paper from colleague Dan Rigby and others from Manchester. This is about expert opinions. So this is about experts again. And they've got two framings, the effectiveness and the practicality of interventions to reduce E. coli, foodborne illness. So 30 interventions, so this is an example where there's a large number of interventions, 31 experts interviewed, and they did they asked them all the questions, in the normal way across their 30 items. The first one was about, well, how effective do you think, which is the most and least effective of these interventions? And then they repeated the process and just asked the same group, okay, how practical do you think these interventions are? And so what they can do, which I think is a really neat way of thinking about this, is that they can start to plot those against each other. So this is actually on the scores rather than on the probability measures. They've normalized the mean effectiveness and practicality scores, but what this gives you is some idea of, in this case, interventions which might be both effective and practical. So what you want is you want to be in this quadrant here. Ideally, you want to find an intervention to prevent foodborne illness which is both effective and practical. The ones you definitely want to avoid are interventions down here which are neither on their basis effective nor practical. And then there's some interesting issues as to when things start to move away, well, as to how to make, say, trade-offs in this space here. So here they've got an intervention which is highly practical, they believe to be highly practical, but not that effective, and they've got another one which they think is very effective but doesn't score highly on practicality. I believe that 19 was, I think that was freezing all foods in order to kill the disease before retail. So maybe it seems to be incredibly effective, but just not practical, may not be practical to do. So this is starts then to map out what interventions they might want to look at and which ones one might want to certainly start to avoid in terms of proposing. So this idea of doing it across multiple framings and then comparing, I think, is really quite powerful. So I think we've got another section, a couple of sections left. We may just pause there and make this a short one, and then we'll finish up in the next